Okay, lesson number 4 has to do with trigonometric identities. So the next couple of lessons that we do in this chapter have to do with proofs, which is never a fun thing. The average senior high math student does not go, yay, proofs. But they are interesting because a proof establishes kind of a pattern that can be used no matter what the numbers are, no matter what the circumstances are. So the first thing that we need to do is we need to clarify the difference between an equation and an identity. So 2x squared plus 3 equals 11 is an equation. It's only true for certain values of x. If x equals -2 or +2, I have a true statement. For every other number, this equation would be false. X plus 1 squared, which when I expand it out gives me x squared plus 2x plus 1, is an identity, because no matter what value of x I put into the equation, the left side will always equal the right side. Whether x is a number, another variable, it could actually be even a binomial expression, it could be an irrational number. It will always be true no matter what the value is. And when we're proving something, we are trying to prove that it is true for all values with the known information that we have. At this point, we already have some basic identities, some things that we know as being true. Our SOHCAHTOA, sine is opposite over hypotenuse, which when I'm on the unit circle is y over r. Cosine is x over r. It is the adjacent over the hypotenuse. And then tan, opposite over adjacent. And so that would be y over x on my unit circle. And then I have the unit circle equation. X squared plus y squared equals r squared. In addition, we also have the reciprocal trig functions, where cosecant is 1 over sine, secant is 1 over cos, and cotangent is 1 over tan. So we're going to use these basic identities to prove the first two identities, which we call the quotient and the Pythagorean identities. So when we are looking at proofs and we are verifying identities for a particular case, what we want to make sure of, again, there are some certain truths that we have to hold to. First of all, when we are doing a proof, we work on the left side and the right side independently from each other. We do not cross sides. So we cannot move something from this side to the other side. That's not allowed. We think of the two sides as having a wall in between. And then if we're verifying, again, when we're verifying, that means that we're putting a number in. We verify the left and the right-hand side separately from each other. Now, showing that something is true, that a value is true for a given identity, does not prove the identity. It just proves that it's true for that given value. So if I look at class example number 1, tan x equals sine x over cos x. If x is equal to 60 degrees, and we go to prove this, on the left-hand side, I would type in tan 60. And tell me what is the exact value of tan 60. And also tell me, how do I get that exact value? So first of all, what mode does my calculator have to be in? So I need to be in degree mode. And then I press tan 60, and I get this number. What number system does this number most likely belong to? Really, it belongs to one of two. Either it's a rational number or it's an irrational number. If it's rational, it means I can put this as a fraction. So if I try to math frac it just to make it easier, nothing happens. So now I can possibly make the assumption this could be an irrational number. How do I I make irrational numbers look nicer? Square it. If I square it, I get 3. But now I have to undo that squaring. So the simplified, or the exact form, would be the square root of 3. Because what I do is I get this 1.73, which I square it, and then I square root it. And the squaring, oops, sorry, not cube root. The squaring and the square root cancel each other out. Okay, so now let's look at the other side. Sine 60 over cos 60. So what is the value of sine 60, the exact value? What decimal do you get?
We need 6.
So I get this 0.8660. So square that number, and then square root that number.
I wrote root 3 over 2.
Root 3 over 2. Okay? And what about cos 60? What do you get when you type in cos 60?
0.5.
0.5, so 1/2. And if I take root 3 and I divide, or sorry, root 3 over 2 and I divide it by 1/2, remember I told you the other way I can divide fractions. If the denominators are the same, I divide the numerators. Root 3 divided by 1 is root 3. Okay, so now we're going to look at the next one. Tan squared x plus 1 is equal to secant squared x. We are going to verify this for the value of pi over 6. So tan squared x means tan pi over 6 squared. So on my calculator, what's the first thing that I need to do? Change to radian mode. Then what? What would I do next?
Tan pi over 6 squared.
So tan pi over 6. And then I square that. And I get 1/3. And if I add 1 to 1/3, what do I get? 4/3. Okay? Then we have secant squared x. So that would be secant pi over 6 squared, but I don't have a secant button on my calculator. What do I have on my calculator? Cos. So this becomes 1 over cos pi over 6 squared.
And also, since I'm not going to be here for Monday, so except for that, we'll get you copies.
So if I type in cos pi over 6, and then square it, I get 3/4. So I have 1 divided by 3/4, which would become 4/3. So I don't need to square root it this time because I'm actually squaring this equation. This is part of the quotient and the Pythagorean identities. So what we're going to do now is we're going to prove them. Okay? The difference when we prove them is we don't have any of these numbers. We don't have 60 degrees. We don't have pi over 6. But we still work the same way. We still treat the left and the right-hand sides differently. Sometimes it's easier to start with the more complex side and try to simplify it to the other side. Sometimes you have to kind of work on each side at the same pace. Things to remember, we do not assume the answer by writing the left side and the right side at the start of the proof, and we do not move terms from one side to the other side. So it says, use the basic identity to prove that tan theta equals sine theta over cos theta, where cos theta can equal 0. Why do I have the restriction that cos theta cannot equal 0?
You can't divide by 0.
Right. So cos theta can't equal 0 because we can't divide by 0. So the basic identities are the ones that were on the front page. The y over r, x over r, y over x. Using these basic identities, how can I express tan theta? How can I write tan theta? Y over x? Okay? I can't really do anything else at this point in time. It's pretty much as simplified as it's going to get. So now if I look at the other side, sine theta over cos theta. Again, using those basic identities, how would I express sine theta? Y over r. And how do I express cos theta? And when I go to divide these, what do I get? Does this show that the left side equals the right side? And because I actually have not used numbers, this becomes an identity because this is going to be true no matter what my x and my y values are. So we use the same type process and we are going to prove that 1 plus tan squared a is equal to secant squared a. So we have our left side and we have our right side. And remember, tan squared a is the same as tan a squared. So if I were to take tan and write it as its basic identity, what would I get? So what does tan equal? Y over x. So if I square y over x, what do I get? Y squared over x squared. If I wanted to add these together as fractions, what would I need to do to the 1? In other words, how do I add fractions? What do I need? Common denominator. So if this denominator is x squared, what's my common denominator going to be? X squared. So how do I write 1 as a common denominator with x squared? X squared over x squared. So now, what's x squared? I get x squared plus y squared over x squared. Go back to that page with the basic identities and tell me if you see a line that has anything to do with x squared being added to y squared. Equals r squared. Equals r squared. I can stop at this point because there's nothing more that I can do. I can write r squared as x squared plus y squared, but then I'm moving backwards. So there's not really any other simplification that I can do. So now we work on secant. What do I know about secant?
Reciprocal of cos.
So the reciprocal of cos. So secant is going to equal 1 over cos squared A. What does cos equal? X over r. And when I square x over r, what do I get?
X squared over r squared.
And if I go 1 divided by x squared over r squared, what do I get? R squared over x squared. Have I shown that the left side is equal to the right side? Yes, I have. Okay. We can also use these identities, these basic identities, to prove the following 5 things. We can, or sorry, I think we already proved this one. We already proved tan x equals sine over cos. Using the basic identities, we could prove that cotangent equals cos over sine. We already proved this one. We can also prove 1 plus cotangent equals cosecant, and sine plus cos equals 1. Sine squared plus cos squared equals 1. Okay. With these 3 identities, there are 6 other ways that I can write these, because I can rearrange them. I can write cos by itself by moving the sign to the other side. So I could rewrite this as cos squared equals 1. I could also write sine squared as being 1 minus cos. I could take this one right here and I could say tangent squared is secant minus 1. Or 1 equals secant squared minus tan x squared. So your formula sheet gives you these 2, and it gives you these 3. But with these 3, you have to realize that sometimes they're hidden in different forms. Okay? You're going to use basic trig identities to prove only the quotient and the Pythagorean identities. So we're only going to use the x, y, and r to prove what's just above here. Everything else, we're actually going to use these things to help prove the other identities. So what I want you to do right now, and I'll give you probably about 10 or 15 minutes, is I want you to look at question number 4 and 5. So with question number 4, It says use the basic identities to prove the identities in question 1 and 2. So you're going to look at 1A and you're going to prove that instead of the verify. And you're going to prove 1B and you're going to prove the identity in question 2. Okay, so we are going to use the identities that were on the previous page to prove or simplify trigonometric expressions. So if we have sine squared x over cos squared x plus 1, we have a fraction being added to a whole number. So we need to convert these both into fractions. In order to be able to add them, I need to add them as fractions, which means I need to write 1 as a fraction with a common denominator. So what common denominator would I use? What denominator do I already have? Cos squared x. So I'm going to change 1 into what?
Cos squared x over cos squared x.
So now I've got this sine squared x plus cos squared x all over cos squared x. So if you were to look at your formula sheet where you have these trig identities, or you were to look on the previous pages, do we have a statement about sine squared x plus cos squared x? It's equal to 1. So now I have 1 over cos squared x.
Yeah, it's because it's hard.
And what do I know about 1 over cos squared x? Look on your sheet.
Secant squared x.
It equals secant squared x. So I've taken an expression and I have simplified it into a single trig ratio. Okay, so let's look at B and try to do the same. What should I do for B?
Well, cotan is 1 over 10.
Okay, it's 1 over 10, and what else is it? Look on your sheet. It's not just that it's 1 over 10. I can write it as something else.
I don't know how to work.
Right there.
Cos over sine.
Cos over sine. So do I want to write cotangent as 1 over tan, or do I want to write it as cos over sine?
I like that.
Why?
Oh, seemed right.
Why does it seem right? What else is in the question?
Well, you have cos and sine in the question.
I have cos and sine in the question. So the idea being you're trying to make it simpler. Putting in another term or another expression is not going to make it simpler. So I've got sine x plus cos x over sine x times cos x. What's cos x times sine cos x?
Cos x squared.
Cos x squared. So I've got sine x plus cos squared x over sine x. How would I add these together?
Common denominator.
What would my common denominator be?
Sine x.
Okay. So if I make this over sine x, it means I multiply the top and the bottom by sine x. So the bottom becomes sine x. What does the top become?
Sine x.
Sine x squared. So now I can add these together, and I have sine squared x plus cos squared x, which equals 1. So now I have 1 over sine x what is 1 over sine x?
Cosecant.
Cosecant x. It's kind of cool. You took an expression and we wrote it as one single ratio by using the trig identities to simplify and to substitute. Let's keep going. Express 2 tan a over 1 plus tan squared a in terms of sine and cos and write in simplest form. Ignore the part in terms of sine and cos and let's just write this in simplest form. So take a look at your identities. Take a look at what is on the page and tell me what your first move could be.
Could you replace tan a with and tan squared a with sine cos?
I could. Is there any place the 1 plus tan squared a? Do you see that anywhere on the sheet?
Yeah. Secant squared
So I've gone from having 3 terms to now having 2 terms. That's a step closer. And now if I look at what Rachel said with my tan, what can I rewrite tan as?
sine.
Sine over cos. So I get 2 sine a over cos a. And what can I write secant squared a as? One over cos. So this becomes 1 over cos squared a. If I have secant squared a, I can rewrite it as 1 over cos squared a. What do I get when I divide these? How do I divide fractions? Okay, I can do common denominators or I can multiply by. I can multiply by the reciprocal. What is that going to give me? Is anything going to cancel?
Cancel cos a.
I can cancel one of these with that. So that would leave me with a 2 sine a cos a on the top and 1 on the bottom. So I guess when I should put it like should write it like this. Times cos squared a over 1, and then I just cross out the 2. Does that make sense? Okay.
Can't you then simplify to sine 2a?
You can. We haven't gotten to that point yet. But yeah, if you look further down, this does become, you said cos 2a? Sine 2a, sorry. Yes. So this could actually become sine 2a. This is a double identity that we'll get into next week. Okay, good. Okay, let's look at number 6. 3 cos 4, or cos to the power of 4 theta, minus 3 sine 4 theta. What could I do first? One thing that you notice.
Can you divide by 3?
Yeah, take out a 3. Okay. Now what? What if I did that? It is a difference of squares. How do I factor it? So how would I factor this difference of squares? What would it become?
C squared minus S squared and then C squared plus S squared.
So C2 becomes cos squared theta. S2 becomes sine squared theta. Okay, now what?
The cos squared theta minus sine squared theta, the difference of squares too.
It's another difference of squares, okay. So when I factor it, what do I get?
Cos theta plus sine theta, cos theta minus sine.
Okay. What about the cos squared theta plus sine squared theta? Can I do anything with that?
That's 1.
That's equal to 1. So 3 times 1 is 3. So 3 would equal, it would be 3 times cos theta plus sine theta and cos theta minus sine theta. Okay, last one. What's the first thing you do? Now what would you do?
Oh, factor out S squared.
Factor out an s squared, which in this case is sine squared. So if I factor out a sine squared theta, what am I left with?
One plus cos squared theta.
What'd you say, Maria?
That's cosecant squared.
Okay. What's cosecant squared?
You have 4 for
I don't.
I just said, how didn't she say you have it? She said she signed something and you have it. I don't know where it is.
Cecilia's asking for it? Or?
Gold months for fill it out.
Start with that and I'll get the other one.
I don't know what to do next.
What's cosecant?
I know for sine squared theta.
Cosecant is 1 over sine squared. What happens when I take sine squared and multiply it by 1 over sine squared? I get 1. It's kind of cool. I started off with a whole bunch of stuff and I ended up with 1. You have to go in with like a really great attitude with proofs. They're fun. Not really. Okay. to 17.